I've said that those opposite side lengths are parallel, and I want to prove that opposite sides are equal. Now that I've drawn in two triangles, hopefully some gears are thinking of like, oh, I'm going to prove that these two triangles are equal. Once I'm done proving that these two triangles are equal, then I'm going to be able to prove that their corresponding parts are equal, which is going to be your opposite side lengths. I, though, first need to prove that they're equal. And the only thing I'm given is parallel lines. Parallel lines can only then give us angles are equal. So I'm going to then start talking about angles. I am going to label my angles. One and two are equal to each other, and 3 and 4 are equal to each other because of alternate interior angles. Okay, so that's 2 angles of the triangle. I need to have a side length between those 2 triangles in order to prove that they are equal to each other. Thankfully, I have my reflexive property here, BD. They are equal to each other because of the reflexive property. And that's my side. So now I can say that ABD is equal to triangle CDB. Just trying to match up those corresponding parts. The reason is angle, side, angle. But that's not what I'm trying to prove here. What I'm trying to prove is that opposite sides of a parallelogram are equal. So I'm going to say now that AD is equal to CB. And I'm going to prove that AB is equal to CD. CPCTC. And you're done. We want to prove that the perpendicular bisector theorem, that if a point lies on the perpendicular bisector of a segment, then that point is equidistant from the opposite endpoints of the segment. Drawing in the idea, we've got a segment A, B, and then we've got C, D, which is a perpendicular bisector of that segment. And then we want to say that any point on that perpendicular bisector will be equidistant to A and B. So I'm going to put a point somewhere on this line, and it doesn't matter where. I could put it above AB or I could put it below AB, but either way, inherently, I'm going to be placing it somewhere differently than you're going to be placing it, which means that we're going to be proving this no matter what. And I want to prove that the distance between this point and B and this point and A will always be equal. I've created 2 triangles. Now I'm saying that I want those 2 triangles. Now I want to say that those 2 pieces are equal to each other, which they're corresponding parts between these 2 triangles. I'm probably proving that these 2 triangles are equal. So first, let's go ahead and set up our proof. We're going to say that CD is the perpendicular bisector of AB. Given. Perpendicular bisector has two pieces. It has the fact that it's perpendicular, and it also has the fact that that segment's been bisected. Perpendicular means 90-degree angles. Bisect means that it splits those two pieces splits that segment into two equal pieces. I'm going to address both of them into. No, I can do it in the same statement because it's the same reason. And the reason is definition of perpendicular bisector. I'm going to label this point right here as F. And I'm going to say AF equals BF. And I'm also going to state that AFE is equal to BFE. Angle A, no. I'm going to say that angle AFE is equal to 90 degrees and angle BFE is equal to 90 degrees. Sorry, end of the day, feeling a little bit tired. Definition of perpendicular bisector. Okay. I've got 90 degrees and 90 degrees, and I've got that those segments are equal. I want to prove that these two triangles are equal, but I want to know, how am I going to prove that these two triangles are equal? Do I want these two 90-degree angles to be equal to each other, or do I want these two 90-degree angles to prove then that they are right triangles? So do I want to do HL, or do I want to use it as an angle between two triangles? I'm going to try and look for other things that I have. And the only other thing that I can see that I can use is that I know that FE is equal to FE because of the reflexive property. As a result, that would give me SAS. So I need to then say that those two angles are equal to each other. So I want to use them as an angle being equal to an angle. Transitive property of equality. And now I've set an angle here. Here I've said a side. And now I need to say my final side, which is FE. Now I can say that those two triangles are equal to each other, FAE. And FBE because of side, angle, side. But that's not what I want to prove. What I want to prove is that AE and BE are equal to each other, always. And I can do that now because I've said that those triangles are equal. So now I can use CPCTC. AE. and you're done. You have proven what you set out to prove. All right, this is the end of our triangle congruence lessons. We're going to have, I believe, I'm going to see how you guys are doing by this point. So I'm still a few days out from you actually taking this lesson. So I'm going to probably see how well you guys are doing on your exit tickets and see if you guys need additional practice. We're going to step it up. We're probably going to take one day. If you don't need additional practice, then we're going to take that day to be like, here are some like actually really challenging triangle congruency proofs, or proofs that include triangle congruency, but then prove other things. And then from there, we're going to move on to our last idea of this chapter. And the last idea of this chapter, our last lesson, in fact, is about similar triangles. So how do we prove that triangles are similar, not congruent? All right, good job.